And now, the moment you've all been waiting for, section 2.6, the definition of the derivative. So derivatives are one of the main things we're going to deal with in this course, and here's our first introduction to them. So I'm going to first remind you of one of the major motivations I talked about at the beginning of class for the invention of calculus. How do you find the slope of a tangent line to a curve? And why would this be an important question? So we're going to start by looking at a relevant example of how this could be important. So suppose you have a train moving on a straight track, and its position function, the distance in feet at any time x, is given by 2x cubed. Okay, so this means that at 0 seconds you're plugging in 0 for x, and you're getting it's moved 0 feet because it hasn't started moving. When you plug in 1 for x, that's after 1 second, it's moved 2 feet. After 2 seconds, it will have moved 16 feet, etc. It keeps moving forward and forward. The question is, how do we find the velocity at 5 seconds? If I plug in 5 for x, so d of 5, 5 cubed is 125 times 2, that's 250 feet. That means that it's gone a distance of 250 feet, but I want to know what the speedometer on that train is actually telling us at that exact moment at 5 seconds. So the way we could do this is we could calculate the average velocities as we get close to 5 seconds. So average velocity is calculated the following way. You do d of b minus d of a divided by b minus a, where a is your starting time and b is your ending time. You may have seen this in pre-calculus. So for example, if we wanted the average velocity, let's say from 5 to 7 seconds, so between the time of 5 seconds and 7 seconds, what is the average velocity it's gone during that time? That would be d of 7 minus d of 5 divided by 7 minus 5. So this is the distance at 7 seconds minus the distance at 5 seconds divided by 2 seconds. So you're finding the feet per second over those 2 seconds. When I plug in 7 for x here, I get 2 times 7 cubed minus 2 times 5 cubed. And 7 minus 5, of course, is just 2. This comes out to being, this is 686, this is 250. When I do that subtraction and divide by 2, I end up with 216 feet per second. Of course, 7 seconds is pretty far away from 5 seconds. So if I wanted a better approximation, I could do just 5 to 6 seconds. So this would be d of 6 minus d of 5 divided by 6 minus 5. And when I do this calculation, d of 6 is, who knows what that is. I plug in 6 for x, cube it, multiply by 2, subtract 250, and then I just divide by 1. This ends up giving me 192 feet per second. Notice the feet is at the top, that's the distance, seconds is on the bottom. So this is a little bit less than what I was getting there, which means as I get closer and closer to the instantaneous time at 5 seconds, it's going to be sort of dropping. And let's do 5 to 5.5 seconds. That's d of 5.5 minus d of 5 divided by 5.5 minus 5. Again, plug this into your calculator, and you end up getting 165.5. Even closer, I could do 5 to 5.1, and when I plug those in here, I end up getting 153.02. And just for fun, how about 5 to 5.0001? This is really close. I would get d of 5.001 minus d of 5 divided by 5.001 minus 5, and this ends up giving me 150.03. So what am I really looking for here? I want the limit as x approaches 5 of d of x, remember this number, the first thing I'm plugging in here, the 7, the 6, the 5.5, the 5.001, that number is getting closer and closer to 5. I'm always subtracting d of 5, so minus d of 5 divided by x minus 5. This number is always the thing that I'm subtracting minus 5. And from what I've seen, it was 216, 192, 165, 153, 150. I'm going to guess that it's 150. And I can actually calculate this, though, is the interesting thing. I don't really need to guess. This is the limit as x approaches 5. What is d of x? Well, according to our formula, that's 2x cubed. And d of 5, we did a bunch of times up here, it's 250 divided by x minus 5. Now this looks a little bit strange, but I can factor out a 2, and I get 2 times x cubed minus 125, which some of you may recognize as the difference between two cubes. And there's actually a formula for how to factor that. You could use polynomial long division, recognizing that 5 is a root, or you could use the formula, which is that it factors to x minus 5 times x squared plus 5x plus 25. And then this x minus 5 will cancel from top and bottom. And now I can actually plug in my 5 for the limit, and this will give me 5 squared is 25, that's another 25 plus another 25, that's 75 times 2. The limit does in fact equal 150. Now before we move on, I want to mention what's happening here graphically. So we've got, hey, come back. We've got 5 here, and we've got, let's say, 7, and our curve looks something like this. So the first calculation I did, here my y value, this is 250. The first calculation I did from 5 to 7 seconds, I was actually finding the slope of that line right there. That's what an average velocity is. And then I said, well, what happens at 6? And I got that 192 come back. That was that line right there. These are all called secant lines, by the way. And as this x value from 7 to 6 to 5.5 to 5.1 gets closer and closer to 5, what I'm going to end up getting when I take the limit of that is this tangent line right at that point where x is equal to 5. And I'm going to get the slope of that tangent line, which is exactly what I'm looking for, and it turns out that that value is 150. So this calculation that we just did is what's called a derivative. It gives an instantaneous rate of change of a function, or equivalently, the slope of the tangent line at a given point. So in definition 2, this is exactly what we had before. We have f prime of p is equal to limit as x approaches p, f of x minus f of p divided by x minus p. In our example above, p was actually equal to 5, right? So we had d of x minus d of 5 divided by x minus 5. So the p was just 5, and we had a d instead of an f. And in general, like the picture I just drew above, what you've got here, there's your p, and here's x, and we're calculating the slope of that line right there, which you can think of as the rise, f of x minus f of p over the run. And we want to get this x value closer and closer to the value of p. And this is the definition that we have. And I mentioned that it also gives you the slope of the tangent line at that point. Definition 2 is great, but it can be cumbersome to calculate. So we have an equivalent definition that we usually use for calculation. It's the limit as h goes to 0 of f of p plus h minus f of p divided by h. And to give you a sense of why this makes sense, why these two definitions give you the same thing. Let me draw this same picture that I've got up here, but now I'm going to use the H notation. So what's going on here, this is my point P, here's f of P. What I'm going to do is I'm going to go a certain distance from P, a distance of H, and that'll take me to the point P plus H. Okay, and now I'm going to find the slope of that line right there. That's the rise over the run, so f of P plus H minus f of P. That's the rise. And the run is just H. That's how far we go. Okay, so that's where this comes from. And it turns out this is a little bit easier to calculate that limit than it is to calculate the one above. If you really like this one up here, you can use it. This is fine, but this is the one that I will use for most of the